Hey, hello, college algebra students. We're getting toward the end of chapter 5. It's section 5-6 is the last section, exponential growth and decay. So we've been learning about these exponential and logarithms. And anyway, we had this formula earlier about money deposited at a certain interest rate. If it was compounded continuously, then we had this formula, A equals P e to the RT. That P was always the original amount of money, and the R was the interest rate. You leave it in for a certain amount of time and years, and E is our famous number, E, 2.7. It's a button on your calculator. So you could watch how money grows. But populations grow like that if they're growing continuously at a continuous rate. Radioactive substances decay like that. They can, instead of growth, you can have exponential decay. Some things depreciate like that. The value depreciates exponentially. So this is the formula for money. But here it is. We tend to use this formula for other populations or radioactive decay, and actually they'll switch it up. Instead of y, they'll use the population as a function of time. That c, they'll use like some p with a subscript 0 is the original population, and then this k is the growth rate. Instead of an interest rate for your money, it's a growth rate or it's a decay rate. If it's decaying, it's a negative number. If it's growing, it's a positive number. That's the k. That gives you your exponential growth if k is positive, or your exponential decay if k is negative. So like I said, they use a lot of different letters, a lot of different, but it's the same formula. I hope you understand that. This is the starting amount. This is the starting amount of money. This is the starting population. So it's the same formula. And I don't know, in calculus and some of it, we use this quite a bit. So I'm using this. And so here's a little problem I made up for you. In the year 2010, which we call year 0, we're going to start time then. In 2010, the population of Marion County is 300,000. And I just made this up, by the way. So I'm telling you the original population. So that's the starting amount. That's the C. So I'm giving you the 300,000 is the C. And I told you that it's got a growth rate, and I like to use the word continuous. I didn't use that here, but that word continuous sort of implies you're using this formula, if you remember. So it's got a continuous growth rate of 3.42%. So that's my K. So that's E raised to the 0.0342. You got to remember to take these percents and make them a decimal when you use these formulas. And then here's the time t, and then this will be the population of Marion County as it grows. Now, I didn't ask a question here. I think the question is going to be this. What is the population today? What is the population today? And so that would be 2020. And if 2010 is year 0, then 2020 would be year 10. T equals 10, you make that little adjustment, and you plug in a 10. And we find the population of Marion County 10 years later. Let's see what it is. E to the 0.0342 times 10. So hopefully you've been working in this chapter a little bit. You got to practice using your calculator. I need my glasses and my calculator, and I can finish this problem. What I do is you can do it a couple ways. You can take the 0.0342 and multiply by 10. That changes that to a 0.342. It moves the decimal. But now I have to E that number. So I'm going to my E button and E that answer. And I'm going to hit enter. And now I got a 1.4077. But now I multiply by the 300,000 times the 300,000. And I get my answer. 422,328.1 person. So we could round off that 0.1 person, just call it 328. So that was good. Now, here's another question I'm going to ask you. How long does it take to double? We're talking about the same problem. How long will it take to double? So I guess in 10 years it hasn't doubled yet. It's at 422,000. In order to double, of course, it would have to equal, we're looking for the time when it equals 600,000. So, I'm changing, I'm going to get rid of this. I need a little room here. But that's a typical question. 600,000 equals 300,000 e to the 0.0342, but this time I don't know the time, and I'm looking for the time it takes for this to double. So I'm solving for t. Well, we've been practicing this. We solve for t by taking the log of both sides. Hold on. You don't take the log yet. First you get the e by itself. You divide by the 300,000. You divide by the 300,000. You know it's going to double. That's going to be a 2. That's 2. E to the 0.0342 times t. Now you take the ln of both sides. The ln of 2, I'll punch that in my calculator later. I took the ln of the other side, and maybe you remember, I'll write this out for you, but you should remember that the ln and the e cancel each other out. And I'm left with 0.0342 t equals this natural log of 2. I divide by that decimal. So I can do all this work without a calculator until the end. And then at the end, I like to punch this in my calculator and to get the number of years. You know, I don't know, it might be 20, 10, 15, 20 years. I don't know what this is. Here I go. The natural log of 2 is a decimal. I put that, there it is, and I divide by 0.0342. 20.267. These are years. I might round it to 20.3 years. So in the year 2030, we'll have doubled our population to 600,000. Okay, I'm going to change this. I want to show you something. What if the growth rate, I'm changing the growth rate. Let's slow it down a little bit. Let's let the growth rate be let's let the growth rate be 2.36%. And let's say I never did measure how many people are in Marion County. And I just want to know how long what is the doubling time? I'm looking for the doubling time. I'm making up a question here as I go, but there's some questions in the homework like this. So, but what's interesting about this is you don't know, I'm pretending I don't know the original amount. So I don't know the original amount. I do know the growth rate, 0.0236, the growth rate times t. And I don't know the original amount, but if I'm looking for when it doubles, then what y value do I put over here? You know, when it was 300,000, you put 600,000. But when it's just some unknown starting amount called c, then what do you put over here? 2c. And for just a brief second, you think, uh-oh, there's too many variables. I can't solve this with too many variables. But step 1 is you divide by c, divide by c. The c's goes away, and there is not too many variables. This turns into the 2 for doubling time. This is a 2, and it's e to the 0.0236t. And you solve. You take the natural log of 2. That kills the e, 0.0236t. You divide by the 0.0236. So I was pretending this is the doubling time for the same county, but I had a lot less growth rate. Remember, I had a lot less growth rate, so this is going to be a longer time. I'll pick up my calculator and check this out. The natural log of 2 divided by 0.0236. Yeah, 29.4. 29.4 years. And like I said, I was pretending I gave you the growth rate and asked you for the doubling time, and I didn't even give you the initial population. So that's the idea is you can find the doubling time, you can find the halving time, you can find the tripling time, even if you don't know the original population, because you can set it up like this, divide by c, and it's gone. You don't need that original population. You do need the growth rate or decay rate. You know, with radioactive substances, they talk about the half-life. And the half-life is how long it takes for it to decay into half the amount it was. So let's say the half-life was 3,700 years. I'm not sure what kind of substance this is. It's radioactive and it's losing half its stuff every 3,700 years. Can you find the decay rate? Can you find the decay rate? Well, let's see. I've got this formula. This is my formula. I don't know the original amount of stuff. I don't know the decay rate. I do know that when I plug in 3,700 years, how much stuff will I have now? I'll have half the amount of stuff. So if you divide by C and divide by C, C's go away, you get a half. And this time I'm looking for K. This time they gave me the time. I made up this problem, and I'm looking for the growth rate, or I'm sorry, in this case it'll be a decay rate. It should come out negative. Let's see. I'll take the log of both sides, the natural log of a half. When I take the natural log of this E, it will cancel. I'll have K times 3,700. When I divide by 3,700, there's K. The natural log of a half divided by 3,700. Again, I'm going to pick up my calculator and see what this is. The natural log of 0.5 is a negative number. And then when I divide by 3,700, it is a teeny little decimal. Oh, in fact, my calculator gave me scientific notation there. Let me show you. It gave me negative 1.8 and then and it said E negative 4. That's scientific notation. That's times 10 to the negative 4. That's negative 1.8 times 10 to the negative 4, which means I can move it's a teeny little number. I can move my decimal over 4 places, which means it's a negative 0.00018. Wow. I wonder what the percent is. That's the K. If I move the decimal over, I can make it a percent. 0.018%. Wow. 0.018%. That's interesting. All right, I made up that problem. You got some better problems in the book. All right, good luck. Try some homework.